Guys, you let me know. Can you see this? Can you see the PowerPoint? Can you see me? Brilliant. Okay, great. So yeah, sorry about that. That was not intentional. Literally just stopped working the very moment where we started this. So sod's law. Anyway, welcome. I know yesterday when we did errors and checking, I imagine some of you might have been thrown a little bit by all the work we were doing around looking with the pseudocode, trying to debug it. Today's lesson, we're actually moving on a little bit from that. We're looking at actually how you take the code that you write in, say, Python or Java. How do you take that code and turn it into what a computer understands? And what does a computer understand? It understands two things: ones, zeros. So we're going to see how we actually get that on here. We need to look at different types of programming languages, low-level languages and high-level languages. They're low and high versus the machine level. So imagine the machine level is at the bottom. Low-level languages are closer to how the machine works. High-level languages are further away from how the machine works. Understand that all programming code must be translated into machine code. So whatever you've written it in, whether you've written it in Python or Java or an assembler, whatever you've written it in, when it goes on the journey to become machine code, it's got to get to that same point. So ultimately, it has to be turned into ones and zeros. And then we look at different ways of, and that's what it's called, translating from high-level code into machine code. There are three main translation methods we'll look at: assembler, interpreter, and compiler. And you know, in everyday life, you hear the term interpreter. And what does an interpreter do? Sits in between two people who can't speak each other's language, and as it goes along, the conversation interprets and translates it from one language into the other for the other person. So we'll be looking at all those today. It's going to be a packed lesson, a lot going on. I might cover most of it today. A lot of it's going to be sort of listening and learning and talking. And then we're going to be doing more activities probably as we go into next week. We'll do some activities today. So yes, what programming languages have you used or heard? Well, we've made use of Python in the programming language, but you know, there are hundreds. JavaScript, Java, Visual Basic. There are literally hundreds of different programming languages. But the ones here that you might have used, like Python, Scratch, and we've heard of JavaScript, they're all considered high-level languages. So they're much further away from how the machine works. And they're easier for people like us to actually write code with. And the first high-level language was designed in the 1950s. I want you to imagine for a moment, back in time, that when we were first using computers like this, how is it that you program these computers? And ultimately, you have to be able to write at the machine level, directly to the machine. So Alan Turing, during the 1940s, cracking the Enigma, when he created that machine that actually helps crack the code, he also, at the same time, had to be able to write code specifically for it. And so what you've got is the idea of somebody understanding how the machine works exactly, is able to write code for it exactly. So they're really coupled together. And what we want to move to is a really sophisticated machine, but if you want to write code for it, you don't have to understand exactly how it works. You can abstract away, and remember, abstraction was removing unnecessary complexity, so you can write code for it. So for instance, in Python, you can say print, open brackets, speech marks, hello, and it will output the message hello. Understand, for that to work at the machine level, somewhere you have to actually store the ones and zeros for each character, whether it's an ASCII or Unicode. Sarah can't join. Sorry, guys. Let me see if I can invite directly to it. You presumably could just click join the meeting, right? It says users already in the call. What? Did that work, Zara? It looks like you're in now. Wicked, fantastic. So we were talking about how computers actually run the code. And so you can write something like, well, if I go up here quickly, you can write something like in in Python, print, and then hello. So that's a high-level language. You can write that command there, and that has to be turned into machine code. So eventually that must be turned into the ones and zeros. And when we have machines like this, you didn't have high-level languages. You had to say things like store each of those letters as the ASCII representation. Okay, you'd have to say name the exact bit of memory it's stored in, and then actually be able to retrieve them individually. You know, that could be 20 lines just to achieve that, and you'd have to know all the ones and zeros to achieve it. Really complicated to do, and so being able to write things like with English and human understandable code has made it a lot easier for people to program. I'm not saying it's easy, but easier. And so the very first computers, all programs were written in machine code. So it was just a bunch of ones and zeros like this. And if you remember, we had the cycle, the processor cycle, where it fetched, decodes, and then executes. So it fetched, decoded, and execute. Remember, that's von Neumann architecture. It fetched what? Well, it fetched instructions. So it fetched what it was supposed to do from memory. It decodes it by understanding what the instruction is supposed to do, and then it executes it by sending it to the ALU. And that cycle goes over and over. And so what's it fetching is something like that. That's an instruction. What is it telling you to do? Well, maybe it's telling you to load the value 1. Maybe it's saying add 6. Maybe it's outputting what's inside this register. This is what they'd have to have done once upon a time. They'd have to have learnt, instead of learning the word load, they'd have to have learned what the ones and zeros are for the command load. Instead of having to write the word add, they'd have to have learnt the ones and zeros for the code add. Imagine how complicated that would be. Maybe there's a couple of hundred instructions. You'd have to learn the ones and zeros for all of them. I mean, yes, they could have a table, but imagine if every single time you had to refer to the table to do an add, or to do a subtract, or to do a store, etc. And then on the other side, the ones and zeros would be the physical space in memory where it's being held. So you can't just be using a variable. So you think something like name equals Bob. Well, when you're doing that, name is a variable, but it has to have created a space in memory to store it, so like a physical address. And that could be, that could be 32 ones and zeros in a row, okay? And then Bob would store it inside it. Imagine having to remember all those ones and zeros. It's so much easier for us with a high-level language to be able to use this, but that didn't exist at this point, so that didn't exist. Fetch, decode, execute existed, but we had to actually, I was not around at the time, learn all the ones and zeros for the functions and all the ones and zeros from being able to actually address the bit of memory you're getting it from. Point being, very complicated, very time consuming, and you have to be a real expert to be able to do this. Real specialist thing. So we had to figure out a way of making it so it's basically almost impossible, or only a fraction of people can do this. And even the ones who can do it, it takes a long time. We have to think of a better way of doing this. And so the first way of doing it is something called assembly language. So assembly language, straight away, you can see that that's not easy to read, but instead of having to learn the ones and zeros for load, you use what's called a mnemonic. So that's a silent M. You use a mnemonic like LDA or ADD for add or STO for store, instead of having to learn the ones and zeros. Straight away, a lot easier. What else? So instead of having to get the actual address in memory, the ones and zeros, you can use a number, or you can use the hexadecimal code to add to it. And so it makes it a lot easier to write code. Now, this is still not easy. This is still quite complicated, but this is an example of a low-level language, so close to how it works, close to how the machine works, but made it a little bit easier. Something else you should point out is that machine code, so the ones and zeros, are specific to the processor. So the ones and zeros for add might not be the same on one processor as another. This is one of the reasons why you have something called the instruction set. On your phones, they use something called the ARM instruction set. And so the ones and zeros for that are the same. Even when you upgrade the processor, what it is to add to subtract stays the same. But on your computer, most likely, you're using what's called x86 instructions. So the ones and zeros are very different. So you couldn't just move code from one to the other. Like the Xbox 360 went up to the Xbox One. The Xbox 360 used something called the PowerPC chip, and the PowerPC had its own instruction set. Xbox One uses x86 instruction set, so you couldn't just copy one from the other. And so when you have back compat, it's actually having to convert it. When you went from the Xbox One to the Xbox Series X or Series S, they're both using the same instruction set, x86. PlayStation 4, same deal, x86, PlayStation 5, x86. You can just push the game over very easily because actually they've got the same instructions. So it's made things a lot more straightforward. So yes, the machine code is specific to a particular processor or family of processors like all the x86 or ARM v7s. And yes, so, and this is an example of low-level code. Let's talk about some examples here. All the bits in green here, I would normally in a lesson be asking you to write down, so I don't know if you've got a note on it, but I'm recording this right now on YouTube, and you can go back and actually make the notes. Assembly language is processor specific, so again, the add, you need to learn the ones and zeros for that particular processor. The subtract, ones and zeros for that processor. Yeah, that's right, Felix, it does. It has to be translated into machine code before it can be executed. Well, AMD has to make use of the instruction set licensed from Intel. So what has to be is that all of the adds and whatever have to be converted. But like machine code, it's also a low-level language. And as we said, things like high-level languages, they work different. I'll come back to this. This is what I wanted to talk through now. So on one side, we have assembly language. And you can see here, that is a human being who's going to be coding it in. So what could it look like? Well, it could look like, whoops. It could look like add, and then maybe a physical address in memory. So add 2F, so that could be an address in memory. And then we could then subtract what's in 2E. And so this would be changing the value that's held in the accumulator. And at the end of it, you could then say output. Okay? So you've got these. These are called mnemonics, silent M. And those, that is an example of assembly language. Now, do you think you could run that directly on the computer? Can you run that directly on the computer? What do you think, people? Completely agree with you. No, because remember, the computer will not understand these things. It only understands ones and zeros. So what has to happen is it is translated from one to another. So it's translated across here. So this is going to be it's translated. This has got a very particular translator though, and it's called an assembler. I think I've spelled that wrong. We'll come back to it. In fact, assembly code is more readable. I think it's got an O in it. Right, I'll come back on that. So it's going to take this code and then translate it to machine code. And what it will do, it will say, look at that, add. And then it will look inside its instruction set. So maybe there is a little tiny instruction set here. So of these different ones. So to add, it will be a certain code. So maybe it's 0110. I've got like a small processor with not many bits. and then sub could be 0, 0, 1, 1, and then out could be 0, 0, 0, 1, etc. So you'd have a long list. That's the instruction set. And you can see here, if I've got add, it looks on my list and it replaces add with that thing there. So the first instruction is I'm going to convert over here, will be 0, 1, 1, 0. But that's only half the instruction. That's the bit that tells you what to do. It's actually called the opcode, but that's not on the spec. This is called the operand, again, not on the spec, and that's the value it's applying it for, 2F. So that's in hexadecimal. And so that would have to be 2 would be 0, 0, 1, 0, and then F would be 1, 1, 1, 1. Now see here, that one line of instructions has been turned into one line of machine code. And then guess what? That machine code would be fetched, and then decode would be like, oh, mean after 0, 1, 1, 0, what's that? Oh yeah, I need to add. Right, that's how that would work. And then it would just go to the next line. So who can write down to me what the next line would look like? Have a go, guys. What do you reckon the next line would be? So the next line for sub, what would it be for sub? So like do the command first of all. Come on, guys, give it a try. So the command was to sub. Where do you see that in the list here? Thank you, Zagal, spot on. Thank you, Felix, spot on. So yeah, I've obviously not explained this very well. I'm trying to do my best, believe it or not. So the next line will be 0, 0, 1, 1. So that's the first bit of the instruction. And then it says to 2E. So who could turn that into binary for me? 2E. Remember, that's hexadecimal. Computer doesn't understand hexadecimal. It needs to be turned into binary. What do you reckon? Also, I'll put the link again. I'll put the link for this lesson because I had to destroy it last time. So in case you want a higher quality version, it is here. Let me have a look. Oh, I see a bunch of questions. So I've got 0010, agree with Louis, Josh, Hussein, and Syra. So I'll put that in here. 0010, and then E, agree with Syra, agree with Hussein, agree with Josh, and agree with Louis. Thank you, people. You've done excellent there. All right. Out. What's out going to be? So the idea being, thank you for saying that, Clarice. I'll have another go at doing this. In the computer, see those ones and zeros there? Those are instructions. I've talked to you a long time ago when we did hardware with processors. I said that there's the fetch, decode, and execute cycle. What is it fetching, decoding, and executing? Here's what it's fetching, decoding, and execute. These. So the processor then fetches that bit of code, that instruction, and then decodes it, executes it, and then it fetches the next instruction. It fetches it, figures out what to do with it, and execute it. Now, Clarice, imagine doing this. Imagine you had to write code. So instead of writing Python or whatever, you had to write code by doing that. How hard would you find it to write code in just ones and zeros? Very hard. I would say I'd find it impossible. It's basically something where it would be so difficult to do. But originally, that was the only way to write code, was direct to the machine in ones and zeros. But that's really difficult to do. And so human beings, programmers, figured out ways to make it easier for people to do. This over here, this is assembly language. And so if we imagine that there's the machine level right at the bottom, assembly language is slightly easier to use. It's called low-level language. Now, instead of having to remember that 0110 means to add a number, I can just write the mnemonic, the word add. Instead of having to remember the ones and zeros for the actual memory, I can just use hexadecimal. Instead of having to remember that to subtract was 0011, I can just write the word subtract, right? So this assembly language is about making it slightly easier, it would still be hard, slightly easier to program. If everyone had to program doing that, I think hardly anybody would be programming. Using assembly made it slightly more easier. Still a tiny amount of people, but it made it slightly easier. And the way that assembly works, that can't run on the computer directly, right? Computer doesn't know what sub is or 2e is. So you have to translate that or assemble that, this is assembly, into the ones and zeros. So you see this one here where it says out. That cannot run on a computer. So you see here, what are the ones and zeros for out? So you see out, you've got out here. This is what's called the instruction set. For out, do you see that there's the binary for what out actually is? There you go. And so what happens in the assembler is it looks at out, it looks in the instruction set, finds out, and then just replaces out with the instruction, the binary code for it. And so what we've just done now is we've started with our original assemble code. Do you see what I mean? That would be easier to remember than that would be. Do you agree with me? It would be slightly easier to program in assembly. Do you agree with me or not agree with me? Good. Do you think it's easier? Let's just say what that could be. Do you think it would be easier in high-level language to say something like 3 plus 2 minus 1 and then print? Do you think that would be easier? Oh, flip. In fact, I should have loaded something into the assembler, but I haven't done it. So do you think it would be easier to go print 3 plus 4 minus 2? Would that be easier to do than to do all of that? Well, right, okay, so this is the point it's making. That is borderline impossible to do, but that is actually what happens at the machine level. We have to get it to that state for it to run on your processor. The first go at trying to make it easier was to use something called assembly language. And so that's assembly language, and it takes this, this mnemonic, like add and sub, and then this hexadecimal value for the memory, and then takes one line and translates it into one line of machine code. Takes one line of assembly code, converts it. And that's called a low-level language. This is even easier, and we'll get to it in a bit. This is a high-level language, but appreciate this one line of code that's in Python, for instance, could turn into maybe 6 or 7 lines of machine code, but we'll get to it in a bit. So for the moment, where were we? We've got, what have we got? We got machine code is in ones and zeros. The specific instruction set will depend on the actual processor. It's very difficult to program doing it. Assembly language is a low-level language because it's close to how the machine works. It makes use of mnemonics for the code, and then it's got this addressing, but it can't run on the computer directly. it has to be translated into machine code. Right, I've got something summarizing it. Do you know what I'll do? I'll leave this for a moment so you can actually make some notes on it, guys, and then we'll move on to high-level languages. So you can make some notes on that, and I will be right back. Okay, guys, I think I'll move on in a bit. Tell me if you guys are ready to move on, though. You know what I'll say, guys? If you're ready to move on to it and you've copied this down, put your hand up. So it'll allow me also to figure out who's actually present so I can do the attendance. So if you're ready to move on to the next slide, please put your hand up and then I'll be able to record who's actually present in the lesson and whether I need to move on now. Okay? So if you're ready to move on, please put your hand up. Thank you, Louis. Thank you, Hussein. Thank you, Brooke. Thank you, Carrie-Anne. Thank you, Salman. Thank you, Sarah. Thank you, Josh. Thank you, Zara. And thank you, Hadi. I'm just waiting on... no, keep your hands up. Keep your hands up. When everyone's hands up, I can move on. Just waiting on Chris, Felix. Just waiting on Chris and Zagal. So, you know, if you need the extra time to do it, that's totally fine. I'm just waiting for you to get your hands up. So you're ready to move on. So I'm just waiting on Chris and Zagal. I don't think you need to write the little bits at the bottom. It's really the top bits. The assembly language is processor specific. It has to be translated into machine code. Chris, Zagal, you almost there? Thank you, Zagal. Just waiting on you, Chris. Hey, Chris, I'm just going to give you another 10 seconds, and then I'm going to need you to put your hand up otherwise, just to prove you're physically here, which I'm sure you are. Okay, Chris, I need you to put your hand up even if you haven't finished copying, just to prove that you're here so I can update my register. Just going to give you 10 more seconds to actually put your hand up, and then we're going to move on. If you don't put your hand up, obviously it's because you're physically not here. It's 5 more seconds, Chris. The next one. Guys, it's saying I've got terrible quality right now. Can you hear me and see me, or have I just glitched out? As in you can see me. Okay, that's great. Okay, moving on to the next thing then. that was human beings' first go at trying to solve the problem of it being very complicated to write that kind of code by using assembly language. But all this is still considered low-level languages. A high-level language, well, they make use of sort of English words like you can have names of variables, things like print. It makes use of mathematical terms. And it's actually, like when you use Python, it's the same idea. When we write pseudocode, we're writing it using high-level ideas. You can make use of selection, so if statements, iteration, while, and for loops. Boolean operators like and, or, and not. And so essentially, high-level languages is what we're learning to learn to program with. And really, I never really learned how to do assembly. I learned it in like a little thing called Little Man Computing, but I didn't learn how to do assembly directly because realistically, it's something that's gone out. Now, it's used sometimes for very specialized bits of hardware, nothing glamorous, but like for instance, let's say you have a washing machine. Now, a washing machine doesn't need to have a full instruction set chip. It's not doing anything complicated. Maybe it needs like 10 different instructions. So it will have a custom bit of silicon, a custom chip, put it in your washing machine. And when you code for it, you don't want to use like Python or whatever. You actually code using assembly to control the very specific things it's doing. It might be the same for a lot of household appliances. Nothing like a TV. Smart TVs are quite complicated these days. But there might be other things like a fridge, for instance. Again, might use low-level assembly language because you're writing code for a specific functions. Okay. So, in what ways are assembly language and machine code the same? In what way are they different? So we'll go over it, but I just want you to think about it for a moment. Well, here are some of the ways that they're the same. They're both low-level languages. One line of assembly code turns into one line of machine code. It's called a one-to-one relationship. Some of the ways that they're different, machine code is only in ones and zeros, while with assembly, you make use of mnemonics and symbolic addressing to represent it. There's a bunch of other ones as well. Oh, both can only be run on a specific, so the assembly language and machine code is for a specific architecture, so a particular chip. So for instance, there'll be an assembler for using the chip inside a phone, like an ARM one, and there'll be a separate one for one inside a laptop. Although these days, actually, the new MacBooks are using ARM. Anyway, and they have this one-to-one relationship. I'll leave this back up, remember it's on my stream, so you can copy this down if you need to. If you can get your notes later. In what ways are they different? Machine code can be run directly on the machine, so it's ready to run. It's ready to be fetched and decoded and executed. Assembly, well, that needs to be translated into machine code using an assembler. Machine code is in binary, but an assembly code makes use of mnemonics. That P should not be there. Oh, I spelled wrong. Sorry. Okay, high-level languages. So we said that they make use of English, of mathematical functions, of selection and iteration, of and or not, so the stuff we've seen, but also they make use of things like arrays, so like storing a bunch of things together and records. And there are many high-level languages, so like Python, JavaScript, Visual Basic. Nearly all the languages you've heard of are high-level languages. And normally a single line of code is turned into several lines of machine code. There are two different strategies. So with assembly language, the only way of converting it was something called an assembler. With a high-level language, there are two strategies you can use. One is called compiler and the other one interpreter. And there are two different ways you can use to translate. But I want you to remember this. I don't care if you started with Python or JavaScript or assembly language, whatever you started with. In the end, it's turned into the same ones and zeros as we did before. They all have to be turned into ones and zeros in the same way. They just take different journeys. When we're talking about high and low level languages, so low is in the hardware level. And then we've got machine code that runs on it, so it's low level, so it's low this way. High level languages like Python and VB are a long way away from how it's worked from that. But assembly language is also a low-level language because it works closer to how the machine code works. So things like Python, Visual Basic, and Java, high-level languages, the ones that are written in English. The ones assembly language where you're using mnemonics and stuff, low-level language because it's closer to the machine level. All right, let's have a go at this. So I'm going to write a bit of code in Python, and then we're going to see what it could look like over here. So we've got input. In fact, let's go back. Name equals. In fact, I'm going to use it with variables. I'm going to use my conventions before. So variables in green. Name equals command input, and then enter name, and then we could say print name. I've invited him in. Thank you for letting me know. I keep on trying to admit, is it not working? Maybe it's stuck on this. Can you tell who's saying I'm trying to invite him? Sorry for the delay, guys. Thank you, Josh. I'll try declining, and then I'll try adding him in. Oh, it says it already exists in the call. I think because he's probably left it, it's not quite forgotten he was here or something. I'm not sure. You can try again, and maybe then I can invite him. Sorry for this, people. So that's a high-level language. Name equals input, enter name, print name. I'm going to do that in assembly. So I'm going to say we need a few commands. So in here we'll need a little instruction set. So I'll do it down here. So instructions. What are we going to need? It's still not letting him in for some reason. Oh, yes, you are. Awesome. Welcome back, Hussein. Yeah, that was strange. Mnemonic. We need to be able to store. We need to be able to input. We need to be able to output with print. And we need to output a message, okay? And then we need, in the instruction set, I'll say that this is the opcode 0110, 1011, and 0111. Okay, this instruction set here, that is just, I've randomly picked things, and it's really small. I should have made that bigger. What I'm doing is I'm saying I'm going to take that high-level language, I'm going to say how it could work in assembly code. So the first thing we did, can you try clicking on the YouTube link then, Hussein, and you could watch it that way? So you can see chat. If you scroll up, you see the YouTube link. In fact, for other people, that may be worthwhile at the moment because it's going to be a bit small. If I wanted to do this in assembly, it's really complicated because I've got a bunch of different functions at the same time. So I need to, first of all, I need to output the message. So I'd have to say in here, out. So this is the assembly language. I have to out, and then I'd have to pretend that that message was stored somewhere in code, like in a memory address. So FD or something. And then I'd have to then say, I'd then be able to have to input that value. Right, so I have to say then input whatever it was. So input something. And then I'd have to store that value somewhere in another location, like, I don't know, 3D. And then I'd say output what was in 3D. All right, let me go through what I'm doing there for a second. So I'm saying this function here in Python is going to print out to you, enter your name. You're going to type in your name, you're going to hit enter, and then that's going to be stored inside name, so in the variable name, and then it's going to print that name out. So it would say like, enter name, I'd say Bob, hit enter, and then it would say Bob. Maybe we should say hi Bob, but we didn't do that. In assembly language, the first thing we have to do is output FD, so I'm saying FD is storing that message there, enter name. Then it'll say input, it'll get the user to input a value, store what that person wrote, so Bob or whatever, in the address 3D, and then output what was in 3D. So those 2 lines there became 4 lines here. Can I run either of these directly on the CPU? Are either of these ready to run on the CPU directly? What do you reckon, guys? My high-level language, could that run directly on the CPU? Or my low-level language, could that run on the CPU directly? If you're not sure, that's fine. It's literally a yes or no answer, so you can try. Do you reckon I could take that code and put it directly on the CPU? No. No. Thank you, Syra. Thank you, Brooke. Hey, either of you, could you tell me the reason why? No. What does a computer understand? What does the machine understand? Ones and zeros. So both this and this need to be translated, i.e. turned into ones and zeros. Okay? With assembly, I go over here and I look at these values and I convert them over into the machine code. I told you there were 2 different strategies. There are 2 different ways you could do it for my apologies, for high-level code. There's 2 different ways you can translate for high-level code. One of the ways is something called a compiler. The other way is something called an interpreter. Now imagine an interpreter. Think about how an interpreter works in real life. You've got one person over here that can speak high-level language. You've got another person over here that speaks ones and zeros. The interpreter, now can I do this? Stands in between the 2. It listens to the high-level language, and the interpreter turns it into ones and zeros. And then it listens to the next bit and turns it over. So the interpreter doesn't try and do all of it at the same time. It looks at a line, it converts it, it looks at the next line, it converts it. So it can look at the first, so let's do interpreter first of all. The interpreter looks at this line, name equals input, enter name. Remember, that's actually going to create these 3 lines of code. So it will say output. So it would be 0, 1, 1, 1 would be the output. And then output whatever that message is. We said FD, so 1, 1, 1, 1 is F, and then D is 1, 1, 1, 0. No? Yes. Yes, I think. Then it would look, it's still interpreting this first line. Then it would have to say, okay, allow somebody to input. So it could be like input 1, 0, 1, 1. Then it needs to store that thing. So 0, 1, 1, 1. So I'm getting that from all here, the instruction set. I need to store it in 3D. So I'll store that in 0, 0, 1, 1, 1, 1, 1, 0. So the interpreter, it's taken, no, I need to make this bigger. What's this going to do? This might go terrible, guys. If it goes terrible, it's not my fault. All right, it's not terrible. So the interpreter, I'm the interpreter right now. I look at that bit of code here, right? The first line, just the first line. And then I convert it, I interpret it, and then I've interpreted that line. Then I look for the next line, in this case, print. And then the interpreter turns that line over here. Okay, so it does it line by line. The interpreter goes line by line and converts high-level code into a machine code. So then it will do the next line, 0, 1, 1, 1. So printing the name at position 0, 0, 1, 1, 1, 1, 1, 0. Now, I want you to remember that code, the assemble code, would have turned into the same machine code. Interpret it from a high-level language. All it did is it did it one line at a time. Finally, there's compiling code. The way compiling works is it looks over all of the code and then in one go generates all the code on the other side. So, assembler only works on assembly language. For a high-level language, you either use compiler or interpreter. An interpreter converts one line at a time as it's going along. The compiler looks at all your code and then converts it over into one go. Okay. I've got a cheesy film because I'm conscious of time. It's coming up to 2, so we've got 15 minutes left. I've got a cheesy film to watch in a moment, but first of all, I think we need to look at the advantages of a compiler and assembler. So these are why we do high-level languages. I want that summarized. Right, here we go. So that's what we've just been talking about. I'll put that on full screen and then you can put your hand up when you finish writing it down. I know it's quite a lot to write, but it summarizes all of it. Let's go over it quickly. Compiler translates the whole program to produce an object code. That's machine code, the ones and the zeros. A compiled code executes faster, yes, because it's all turned it into machine code. It can just run it as it's going along. An interpreter, let's go through two at the time. So compiler all at the same time, interpreter translates and executes as it's going along. Compiler, because it's already turned into ones and zeros, it's ready to run straight away, so it's much faster. An interpreted language, it takes more time because it needs to run every single time. Let me give you some examples. You buy a computer game, whether you're buying it on PlayStation Store or Xbox Store or physically buying the disc. Do you think that code is going to be interpreted code or compiled code? What do you reckon, guys? Considering it needs to run fast. Interpreted code or compiled code? The computer game you're going to buy. What do you reckon, guys? Which one? Was this a bit too much information? You can let me know, guys. I'm ready to hear feedback. Hello? See, yesterday I had a problem with chat where it suddenly switched off, so I don't know whether that's happened or whether everyone's just too nervous to say something. Thank you, Brooke. In fact, Brooke, you know what? Since you just saved my bacon there, I'm going to nominate you for Excellent Student for the Day. I'm sure others as well. I'll go through it. Aren't you in a lesson? Come on, Clarice. Well, you can come back to this anyway because you'll be in this thing. Because you can come back to the YouTube stream. Yes, computer game code is compiled because it runs much faster. If you go to a website, you guys go onto websites, and a lot of you guys do this funny thing when you go F11 or F12, and you can edit the code and make it like web pages say different things. That's because that code's interpreted, so that you can actually, it has to run, because it's different in different devices. You write the code once there, and then you can edit it. So it's really useful for that. No need for the compiler to be present. So once you've made the code, so once the machine code's made, you don't use the compiler anymore. So like when you put your disk in and run it, you don't need the compiler anymore. It's there ready to run. If you're interpreting code, so like a web browser is the interpreter, so you couldn't look at a web page without that web browser there because it's constantly turning that code so you can see it. For a compiler, if you got it compiled, all you're seeing is ones and zeros. You have no idea how it works. You can't really steal the code because it's all in ones and zeros. But interpreted code, like you see when you go F12 on that web browser, you can see how that code works. Right, I'm going to leave that up there so you can write it down, and then I'm going to dig out the video for it. So I'm going to give you. It's going to take you a little while, isn't it? Because there's quite a bit there. I'll give you 5 minutes to get that done. Compiler versus interpreter. And then I'm going to find the cheesy film from the 1970s for us to watch together. Write down these definitions for the difference between compiler and interpreter, Josh. Also, it might be worth just going onto YouTube and going back to this point, so like rewinding. Although bear in mind, when I play the video, I won't be able to play it through. Will I be able to? Not very easily. Maybe I could actually play it through both. That might have been too much time, actually. Any of you guys finished writing that down? Okay, okay. Okay, guys. Hopefully that's been enough time, and if not, remember you can go back to YouTube and then you can rewind and actually go back to that section. I'm going to see if I actually can get this to work.
It does give you a chance to correct your mistakes as you go along. If the mechanic removes the wrong spark plug, for instance, you'll see this happen right away, and you'll be able to change your instruction accordingly. Compare this with the way the second sort of translator, the compiler, goes about his work. He takes your complete list of instructions and without further ado translates the whole lot straight into gobbledygook. He then hands them back to you straight into gobbledygook. He then hands them back to you and goes away, leaving you all on your own. All this has taken some time, but from now on, things will go very fast. You hand the complete list of gobbledygook to the mechanic, and he executes them all in one go. Bang, bang, bang. There's no waiting about this time. But there's one disadvantage to this, of course. If there was a mistake in your instructions, it's too late now. This analogy comes very close to the way the interpreter and compiler translator programs actually work with computers. An interpreter runs slowly, starts right away, and lets you see how things are going. Whereas a compiler takes extra preparation time before your program can run, but then lets it run very quickly and efficiently. To help you remember the difference between an interpreter and a compiler, look at the words themselves. Inter means between. The interpreter is always between your program and the computer, and it translates line by line. To compile, on the other hand, means to pile together. A compiler piles together your entire program and translates the whole thing all at once. Which one you use on planet Gobbledygook is entirely up to you.